Welcome to all the students. I am Rajiv Kumar Soni and I will be taking your third lecture on simple lifting machine. Now the topic with which I am starting is law of machine. This is also one of the important topic. This is important topic and many numericals are based upon this law of machine. Now first of all, to know about the law of machine or how to define the law of machine. Basically the law of machine is a relationship between the load lifted and the effort applied in case of a simple lifting machine. To know the law of machine or to define the law of machine, first of all we have to draw a graph between the effort applied and the load lifted. Now suppose this is a lever arrangement and this is the fulcrum, and you know the fulcrum is the point about which the object can rotate like this. Now suppose this is the load point and this is the effort point. Okay, so this distance is known as the effort arm and this distance is known as the load arm. Okay, effort arm, load arm. This is the effort point, load point, and at the load point a weight is kept W, and to lift the weight we have to apply effort here like this. Okay, now suppose the weight is let it be 10 Newton. Okay, now we have to apply the effort to lift this weight. Now let us assume that machine is a ideal machine, and in ideal machine friction is equal to 0. There is no friction in an ideal machine. First of all, consider it as an ideal machine. So in case of ideal machine, if we want to lift a load of 10 Newton, then we have to apply an effort of 10 Newton. Because no extra effort is applied as the friction is 0. The extra effort only is applied to overcome the friction, and the friction is 0. So for lifting 10 Newton, the effort applied is 10 Newton. Now suppose the load is raised to 20 Newton, then the effort applied again will raise to 20 Newton. Suppose this is 30 Newton, again the effort applied will be 30 Newton. I am considering this machine as an ideal machine. That is why effort and load are equal. Now suppose if we draw a graph between effort and load, suppose this is y-axis, this is x-axis, this is x-axis, and this is y-axis. Okay. Suppose this is the effort. Oh, sorry, this is the load. This axis represents the load and this axis represents effort. Now when the load is 10, the effort is 10. Load is 10, effort is 10. So this will be the point. Similarly, when load is 20, effort is 20, this will be the second point and this will be the third point. So our graph comes to be a straight line like this. This is our graph, and this graph comes to be a straight line. Okay, so the graph between the load and the effort, that graph only tells us about the law of machine. So basically law of the machine is the equation of this straight line. This is a straight line, or you can say the graph between the load and the effort, and the equation of this straight line tells us about the law of machine. That is, law of the machine is nothing but the equation of the straight line which we get in a graph between load and effort. Now as you know that the equation of the straight line is equal to y is equal to mx plus c. Okay, so y, what is y? Y, the y-axis represents the effort P. So instead of y, we can write P is equal to mw plus c, where w is the weight which is lifted by an effort of P. This is the equation of the straight line, and as the y represents the effort and x represents the load, so instead of y we are writing P, and instead of x we are writing w. So this is the effort, this is the load, and m is the slope of the line. What is m? Slope of the line, or you can say the slope of the graph. What is c? Now in this case c is 0. This will be equal to 0, and how it will be 0 you will know a little later. Now suppose initially I considered this machine as an ideal machine, but now suppose it is an actual machine. If it is an actual machine, then there will be some friction. Like suppose there is a friction of 2 Newton here. How much? 2 Newton. Then suppose there is a friction 2 Newton and 10 Newton is the weight which has to be lifted. Then the effort applied will increase a little bit. The effort applied, instead of 10 Newton, it will be 12 Newton. For 10 it will be 12 Newton, because 2 Newton extra effort has to be exerted to overcome the friction. Now if suppose similarly for 10 Newton it will be 12. Now suppose we have increased the weight from 10 to 20, then our effort will also increase. It will be increased to 22 Newton, and for 30 Newton it will be 32 Newton. Okay, so this is you can say 10 plus 2, this is you can say 20 plus 2, this will be 30 plus 2, 10, 20, 30. They are the effort which are applied to lift the loads of 10, 20 and 30, and the 2 Newton extra effort is being applied to overcome the friction, and this 2 will be constant. So if you take these values, that means 10, 20 and 30, and you take these values, that means 12, 22 and 32, then our graph comes to be like this. This is 10, this is 12, this is 20, this is 22, this is 30, this is 30, and this will be 32, like this. This is 10, this is 12, this is 20, this will be 22, and if this is 30, and this will be 32, like this. But you see, in both the cases the graph is a straight line. The only difference is, when the machine was ideal, the graph started from the origin, but when the machine was not ideal, it was a practical machine, then the graph started from this point. Okay, this is for actual machine, this is for actual machine, and this graph is for ideal machine. This is for actual machine, this is for ideal machine. Both the graphs are the straight lines, but the starting point is different, and both are parallel to each other. Even this is parallel to this, only the starting point differs. And this much is the extra effort. So see, this much is the extra effort. In this it is 0, but in case of actual machine the extra effort is 2 Newton. This is 2 Newton. So this 2 Newton of extra effort is being applied to overcome the friction, and for this for this graph, the equation will become P is equal to mw plus c. Okay, this is the equation for actual machine and this is for ideal machine. In ideal machine the c becomes 0, but in actual machine it has some value for c. Now in this, P is the effort applied, W is the weight lifted, M is the slope of the line, and C, it is a constant. And C stands for the extra effort which is being applied to lift the load, which is equal to the frictional force. Okay, it has got the value of 2 according to this machine, but it is always a constant, like this. Here also the difference is 2. In the second reading the difference is again 2. In the third reading again the difference is 2. That means the this value, that is the you can say the frictional value, is constant at all the situations, but effort applied increases as the load which has to be lifted increases. Okay, this equation is only known as the law of the machine. So the law of the machine is equal to P is equal to mw plus c. Effort, this is the weight lifted, m is the slope of the line, and this constant stands for the extra effort which is shown here. This is the extra effort to overcome the friction. Now after this we will study about maximum mechanical advantage. Now as you know that mechanical advantage is equal to W upon P, but the mechanical advantage will be maximum when the machine will be ideal. Okay, so ideal machine will have the maximum mechanical advantage, but for ideal machine P is equal to mw because C becomes 0, because ideal machine the friction is 0, so this extra effort has not to be applied, so C becomes 0. So this is the equation of a ideal machine. Now from this equation P, if you take W here, P upon W is equal to M, and W upon P will be equal to 1 upon M, and W upon P is the efficiency, is the mechanical advantage. So mechanical advantage is equal to 1 upon M, and this mechanical advantage will be maximum mechanical advantage, as we have derived this mechanical advantage on the basis of ideal machine, or on the basis of the equation of an ideal machine in which the C was 0. So for ideal machine, whatever the mechanical advantage comes, that is maximum mechanical advantage, and the formula for the maximum mechanical advantage will be 1 upon M. Now second thing, efficiency. Now efficiency is equal to mechanical advantage upon velocity ratio. Okay, efficiency is equal to mechanical advantage upon velocity ratio, and efficiency, but I have told you earlier that velocity ratio is for a particular machine is always constant, and efficiency depends upon mechanical advantage only. Efficiency is equal to mechanical advantage upon velocity ratio, but it will vary when mechanical advantage varies, because velocity ratio for a particular machine is always fixed. So efficiency will be maximum when mechanical advantage will be maximum, but maximum mechanical advantage is equal to 1 upon M. So efficiency, maximum efficiency is equal to 1 upon M into VR. So this is the formula for maximum efficiency, and this is the formula for the maximum mechanical advantage. If you want to calculate the efficiency in percentage, then you have to multiply it by 100. Then you will get in percentage. So you have to learn these two formulas. One is the maximum mechanical advantage, 1 upon m, and one is the maximum efficiency, which is equal to 1 upon m into VR into 100 if you want to get in percent. Now up till this we have studied everything regarding these. All were the general things about any type of machine. All are the general concepts, general terms, general definitions for all types of machines. Now after this you have to study about different types of particular machines which are in your syllabus. All the machines are easy, but they are particular different types of machines, and for all the machines you have to find first mechanical advantage, then you have to find velocity ratio, then you have to find efficiency. That means you have to learn the formulas for mechanical advantage, velocity ratio and efficiency in case of all the different types of machines. Now this is the first type of machine, and the name of the machine is simple wheel and axle. Okay. Now first of all, if you about its construction, I think the construction is very clear from the figure. Then also I am explaining it. This type of machine consists of two drums. This is first one drum, this is the second drum, and the diameter of this drum is greater as compared to the diameter of this drum, and both of the drums are mounted on a central shaft. They are basically keyed or rigidly attached to the shaft. That means shaft, this drum and this drum, both the drums and the shaft, they work as a single unit. If you rotate this, everything, the whole thing will rotate. This will also rotate, this will also rotate, this will also rotate, because all the three things are rigidly attached to each other. Now see, one string is wound about this drum and one string is wound around this drum. Okay, this drum is known as effort drum and this drum is known as load drum. But suppose if the string is wound in clockwise direction on this drum, and on this drum it will be wound anti-clockwise, clockwise and anti-clockwise, in such a way that when this point comes here, this point comes downwards, then the weight will be lifted upwards, because they both are wound in opposite direction, clockwise and anti-clockwise, or anti-clockwise and clockwise. So when the P comes down, the weight W will be lifted up. Now first of all, in this machine, what is mechanical advantage? The formula for the mechanical advantage is same in any type of machine, which is a general formula. That is, mechanical advantage is equal to W upon P. Now velocity ratio. As the velocity ratio is concerned, its general formula is y upon x. That is the distance moved by the effort divided by the distance moved by the load. But velocity ratio for a particular machine is fixed, but for different machines the value of the velocity ratio will be different. Now in this case, suppose this is not efficiency, changes to y. What is y? Y is the distance moved by the effort and x is the distance moved by the load. Now suppose this is the point and the force is exerted, and we pull this point from here up to such a position that it rotates, it completes its one revolution. Okay, it completes its one revolution. If suppose this completes its one revolution, this will also go through one revolution, and when P comes down, W will be lifted upwards. Now in one complete revolution, so let let us give one complete revolution to this one. In other words, the whole system will undergo one revolution because they all act as a single unit. Now, what is the distance moved by the effort? The distance moved by the effort will be equal to its circumference. Will be equal to its circumference because it has completed one revolution, and this string from here to here will be its circumference, and the circumference is equal to pi d, where d is the diameter of this one. Okay, this is the diameter of the effort drum. Now coming to this, now previously the load was here and the effort was here. Effort came from here to here, and the load will be raised from here to here, and the distance moved by the load will be equal to the circumference of this load drum, not this effort drum but this load drum, which will be pi d, where small d is the diameter of the load drum and the capital D is the diameter of the effort drum. Then y will be equal to pi d and x will be equal to pi small d, where d is the diameter of the effort drum and small d is the diameter of the load drum. Then our velocity ratio will be y upon x, that means pi d upon pi small d. Pi and pi cancels out and it will remain d upon d. Okay, so this is the formula for the velocity ratio, and this is the formula for the mechanical advantage. Now third one is efficiency. Efficiency comes to be, for any machines, it is mechanical advantage upon velocity ratio. So the formula of efficiency and mechanical advantage will be common for all the machines, but different machines will have the different values of velocity ratios, and next machines will be taken in next classes. So thank you so much.